Welcome to the 7th video lecture in this discrete mathematics course. In this video, we will continue with our study of proof techniques. We will look at some of the problems and some new techniques of solving them. So far we have seen that a theorem can be represented as A implies B, where A is a set of assumptions and B is the deduction. There are different techniques, proof techniques, for attacking this problem, namely say constructive proof, proof by contradiction, proof by contrapositive, induction, counterexample, existential proofs, and so on. In this course, we will be going over all these proof techniques one by one and doing each of these proof techniques carefully. Now, we will be doing a lot of problems, and many of the problems will require some of the proof techniques, or in other words, some of the proof techniques will make some of the problems easier. But the main question which will be asked will be that which approach to apply. In other words, which problem should be used, which proof technique should be used to solve which problem. Now this depends on the problem. Some problems can be split into smaller problems and that can be tackled easily. Or in other words, the smaller problems can be tackled easily. Some problems can be viewed in a different way and that can help in tackling the problem. But which problem to split and how to split the problem or how to view this problem is an art in itself that cannot be exactly taught. It has to be learned by you by doing a lot of problems, doing a lot of exercises. We can in this course tell you about the various proof techniques, give you some thumb rules like okay, this kind of problems, for this kind of problems maybe this proof technique is an easier job and so on. But at the end it would be your skill and your creative mind, and that has to be developed with a lot of practice for solving these problems and deciding which proof techniques to apply. So to start with, let's consider one of the most easy case. This is something we did in the last video. Namely, say if I have to prove A implies B and B can be written as C and D. B can be split into two parts. Then A implies B is same as proving A implies C and A implies D. So this can help us in splitting this problem. So for example, we were looking at this problem which says that if B is an odd prime, then 2b square is greater than or equal to b plus 1 whole square and b square is congruent to 1 mod 4. In this problem, B is an odd prime. This is the, of course, A. And b square is greater than or equal to b plus 1 whole square and b square is congruent to 1 mod 4. You can clearly see that this is the C, this is the D, here is an and this whole thing together is the B. So in other words, A implies B can be split up as A implies C and A implies D. Thus, this problem can be split up into these two parts, namely, first part, if B is an odd prime, then B square is congruent to 1 mod 4, and secondly, if B is an odd prime, then B square, 2b square is greater than or equal to b plus 1 whole square. Okay. Now, there can be a lot of redundant assumptions also, and those can be cleaned up. In other words, there can be many assumptions that are not necessary, that only makes the problem more complicated. So if we can throw them, that will of course help us in simplifying the problem. So in other words, if I have to prove A and B, A and C implies B, but I can already prove A implies B, that means this C is a redundant assumption. So in other words, A implies B is good enough to prove A and C implies B. So one would need to find out the assumptions which are redundant and throw them. But which assumptions are not needed is something that only can come in practice and or with your intelligence. For example, the problem that we are looking at already, we had split up into these two problems, first part and second part. Now look at the first part. The first part says that if B is an odd prime, then B squared is congruent to 1 mod 4. We had discussed it in the last video that what property of odd prime do you need here? And as I told last video, that all we need here is that B is an odd number. So the primeness is not necessary. B is any odd number, then B squared is congruent to 1 mod 4. Similarly, in the second part, where we have proved that if B is an odd prime, then 2B squared is greater than or equal to B plus 1 whole square. What is the property of odd prime do we need? We will only need the fact that B is greater than or equal to 3. Well, if it is an odd prime, it has to be greater than or equal to 3. So namely, the fact that it is a prime or it is an odd and so on was a redundant assumption in different cases. So depending on the problem, we might have to throw away some of the redundant assumptions. So in other words, this problem can be written as this problem. So these are good enough problems, meaning this problem implies the other problem. Namely, if B is an odd integer, then B squared is congruent to 1 mod 4. And the other one, if B is a real number strictly greater than 3, then 2B squared is greater than B plus 1 whole square. In this video lecture, we will be solving these two problems. We will solve these two problems using what is known as the constructive proofs. Now, what is a constructive proof? A constructive proof, of course, we prove this A implies B, but the idea is that we don't rephrase this problem in any other way. We just start with A and end with B or something similar of that. There are two cases, of course. Number one is the direct proof where we start from A and end with B. And the second case, which is a case study, where we split the problems depending on A. Now in this particular video, we will be using this direct proof technique to solve both the problems. We will be doing case study problems in the next two videos in this week. And in the next week, we will be going into more complicated non-constructive proofs, which are like proof by contradiction or contrapositive or induction, so on. Now let's start with the first problem. In the first problem, it is told that n is an odd integer. Then prove that n squared is congruent to 1 mod 4. Now if n is an odd integer, that means n is equals to 2k plus 1. Okay, this is a mistake, this should be small n. So small n should be is equals to 2k plus 1 for some integer k. Right? That's the kind of the definition of oddness. that is the case, then what is n square? N square is 2k plus 1 whole square, which is 4k square plus 4k plus 1, which I just collect it as 4 times k square plus k plus 1. So by rearranging the numbers, we get n square minus 1. So by taking this n square and this 4k square plus 1, we get n square minus 1 is equal to 4 times k square plus k. Now let's look at this number k square plus k. Since k is an integer, so k square is an integer, k is an integer, so for k square plus k is also an integer, and hence this expression means that n square minus 1 is 4 times some integer, or in other words, n square minus 1 is divisible by 4, which is just what we mean by when we write the notation n square is congruent to 1 mod 4. Now this is a pretty simple direct proof. We started with the assumption that n is an odd integer. We worked our way through. We did the obvious things. There was an n square sitting there, so we had to square the n, which was, since n was odd, it was 2k plus 1, and we continued like that and we reached our goal. Now things need not be so easy in some times. Things can be a bit more tricky. For example, let's consider the other example that was there. Namely, if b is any real number greater than or equal to 3, then 2b square is strictly greater than b plus 1 whole square. Now how do I prove it? So let me first give you the one proof. So for the first proof, let's start with, okay, since b is greater than or equal to 3, so b minus 1 is greater than or equal to 2. By squaring both sides, we get b minus 1 whole square is greater than or equal to 4. And this 4 is strictly greater than 2, we can write b minus 1 whole square is strictly greater than 2. Now let's try to open up b minus 1 whole square. We get b square minus 2b plus 1 is greater than, strictly greater than 2, which if I rearrange it correctly by taking the 2b plus 1 in the other side, I get b square is greater than 2b plus 1. This plus 1 and plus 2 cancels out and leaves plus 1 behind. So I have b square greater than or strictly greater than 2b plus 1. And now if I add b square to both sides, I get 2b square is greater than, strictly greater than b square plus 2b plus 1, which is nothing but b plus 1 whole square. So now this is also a direct proof. The problem is that this direct proof must have looked a bit magical to you. In other words, we started from the fact that b is greater than 3, but then we did a lot of tricky things. For example, why did we write it in this form of b minus 1 greater than or equal to 2? Why did we even square it? Why did we do this weird calculations of splitting up and all those things? Or in other words, the most important thing is that why did we even consider b minus 1 whole square? Now these can indeed be pretty tricky and they can be magical. Thus, sometimes the direct proof can be magical and hard to understand how to obtain. It's not that the proof was hard, it's just that the proof was magical, right? Proof started from somewhere, ended somewhere, and you would think, if I am asked to solve this problem in an exam, how will I do it? I'm sure you must have faced a similar question in your mind in your high school or in other math courses. Now, there is a simpler technique to attack this problem. this is called the backward proof. Or in other words, we start from the backward and go ahead. So here that means that if I have to prove A implies B, the idea is to simplify B and get something simple. And if in the end I can prove that B is congruent to is equivalent to C, or in other words B and C are same, then A implies B proving that is same as proving A implies C, and which can be easy if I manage to put C to be C as an easy number, an easy expression. So let's look at this problem again. How do we apply this backward proof to this technique? So here, if B is any real number greater than or equal to 3, then 2b square is strictly greater than b plus 1 whole square. So the backward proof of it would be to play around with the b. So this is the b part, right? To play around with this b. So namely, to prove, in this case, what do we have to prove? 2b square is greater than b plus 1 whole square for b greater than or equal to 3. So let's open up these things. We get 2b square is strictly bigger than, by opening up b plus 1 whole square, we get b square plus 2b plus 1 for b is greater than 3. This is equivalent statement. Now I can therefore subtract b square on both sides, and we get b square minus 2b minus 1 is greater than 0 for b is greater than or equal to 3. Now as soon as you get something of this form, what is b square minus 2b, you realize that this has the very flavor of b minus 1 whole square. So this can now be written as b minus 1 whole square minus 2, because this was a plus minus 1 and I should have got my plus 1 also here. So this is minus 2. So b minus 1 whole square minus 2 is strictly greater than 0 for b greater than 3. Now you already see that the expression b minus 1 whole square is coming out not by looking at a, but looking at what to prove, namely b. And this particular expression is actually not that hard to prove. Or in other words, we have to prove that b minus 1 whole square is greater than 2. And this is kind of obvious. Namely, b is greater than or equal to 3, then b minus 1 is greater than or equal to 2. Or in other words, b minus 1 whole square is greater than or equal to 4, which is strictly greater than 2, which is what we have to prove. So actually speaking, this proof and the other proof are identically same, except that one worked with A and ended up with B. The other, we simplified B first before we applied A implies B. So these are the two proof techniques that we have. So in other words, to finish up, for proving A implies B, we can either start with an assumption A and step by step prove that B is true, or we can do the backward proof, which basically means that we simplify B and then prove A implies B. So we simplify B to C, and then A implies B is same as proving A implies C. And since B has been simplified to C, A implies C would be an easier thing to prove. So this brings us to the end of this video lecture. We will be continuing our study on proof techniques, particularly constructive proof, in the next video lecture. Thank you.